We're going to start off with a keynote by Michael Biercuk. He's the founder and CEO of Q-CTRL. He took a break from Bondi Beach to fly from Australia to share his perspective with you. The title of his talk is From Optimization to Error Correction and Beyond. So please join me in welcoming Michael.
Thanks, everybody. It's a real pleasure to be here. Thanks to Malak and the organizing team for having us. In this talk, I know we've heard a lot about use cases. What I want to do today is give you real insights into the state of the art in quantum computing. I want to help those of you who are not experts in the field understand how easy it is becoming to take advantage of this technology for the business problems that matter to you. And because we're a product-focused company, I really want to surprise and delight with something very, very special that I'll share at the end of the talk. Now, if you're not familiar with Q-CTRL, our general idea is that the core to making quantum technology useful is software-level innovation. We build AI-powered infrastructure software to make quantum technology useful. And we do this in two core verticals. One vertical is, of course, quantum computing. Here we build performance management infrastructure software that makes the computers perform better. We work with pretty much all of the major vendors, and I'll share more about that in a few minutes. But in parallel, we have a very large effort in quantum sensing for both commercial and defense applications, where we work with major defense primes, we work with commercial partners and defense agencies to bring this technology to solve really critical missions. I'm going to focus today on the left-hand side. Now, I think all of you in this room at this point in the day should be aware that really one of the biggest bottlenecks in quantum computing is the fact that the hardware tends to fail. It tends to suffer from errors. Now, this is an experience that's completely distinct from our experience with conventional computers, which can run for 1 billion years and never suffer a hardware fault. Quantum computers are generally very fragile. We build software that fixes this problem. We build AI-powered infrastructure software that reduces errors and allows us to get better performance from the machines. But in addition, it does something else. It allows us to abstract. Because for so long, programming and operating quantum computers has required us to really write code at the machine language level or the assembly language level. And that's not how anybody builds applications in the real world. This kind of infrastructure software allows abstraction so we can connect the low levels of hardware up to the high levels in the so-called quantum computing stack. We were very proud that our software went live as the first native integration of any independent software vendor with a major cloud platform provider in quantum in December of 23 when we went live with our native integration with IBM. We then expanded that in December of 2024 as one of the first providers of Qiskit functions. And since then, we've built relationships and announced integrations connecting our performance management software with hardware from not only IBM, of course, but Rigetti, Oxford Quantum Circuits, Dirac, and most recently IonQ. We're very excited to bring this technology to as many platforms, as many qubit modalities as possible. The reason for it is what it achieves. Our focus is on enabling end users to succeed in the problems that matter to them. And foundationally, our technology unlocks latent performance to make things that were previously impossible possible. And we see this from the demonstrations that come from our customers. In this particular case, in peer-reviewed literature, work from Capgemini, from SoftBank, from Deloitte, and others in applications from biopharma and drug discovery all the way through to quantum AI, quantum machine learning. These bits of research, these new business cases for quantum computing exist because our software takes the bare hardware and improves it by orders of magnitude. We've seen 10x improvement in the complexity of the circuits that can be run, measured by something called circuit depth. We've seen 1,000x improvement in the computational accuracy. How likely are you to get the right answer from the machine? We've also seen 1,000x improvement simultaneously in cost reduction. You get 1,000 times better answer at 1,000 times lower cost. That is the winning combination. It is all published in the peer-reviewed technical literature. Behind the scenes, what's happening is we've built a completely autonomous AI-powered tool chain that allows us to reduce errors everywhere that they occur. We have found that intelligent machines are much better at manipulating the hardware than we are, and we leverage them to do everything from crafting a new machine language for the processors up through things like compilation. If anybody's interested in the details of this, please do ask me afterwards. But what I want to emphasize is that each of these parts has been built and optimized for performance and for integrability. They all work together, but you as a user have only one line of code to execute. There are no settings, there's nothing to mess with. It's one line of code to execute this. And this is what Heather West at IBC referred to as frictionless quantum software that allows end users to leverage the skills that they already have in order to take advantage of quantum computing. This is not about learning the details of quantum computing hardware. One of the key problem areas that we've explored that we believe can really bring quantum advantage in the near term is optimization. Optimization as applied to scheduling, routing, logistics. We've heard about this from several other talks before. I wanted to show some true state-of-the-art results of what is actually possible on the largest, most complicated machines today. And this is based on work that we have done with Network Rail in the UK, with the Australian Army and convoy optimization, Transport for New South Wales, and the Airbus BMW Challenge, where we were a finalist last year for plant manufacturing optimization. This is an area that we have invested quite substantially in because it truly looks like quantum advantage is near. So if you're not familiar with this kind of problem, the way we solve optimization problems is generally through what's known as a hybrid quantum algorithm. We have a small quantum kernel, and that's wrapped in a larger classical execution. That's generally in a loop. It's an optimization iterative process. This approach takes the hardest part of the computation and farms it to the quantum computer, if that part of the problem is well aligned with what quantum computers are good at, and by that combination can give huge benefits. The user experience, to be frank, has not been great historically. A user has had full responsibility for everything. It starts with defining the problem and taking that problem mathematically and turning it into quantum circuits that can be executed on a quantum computer. As an end user, that is your responsibility. You then need to figure out how to execute those circuits such that they give you useful answers. That means any performance management, your responsibility. You have to build the classical loop and integrate those two things together such that the classical loop converges, your responsibility. You have to then take the output of the optimization, understand how to interpret that output, and compare that output to the best, to what should be the true solution or the best solution you're looking for. Also your responsibility. And our view is that this is not reasonable. There's too much requirement on the users to focus on the lowest levels of execution. And so now, this is one line of code. You can execute all of this via our optimization solver with one line of code. And as an example of what was enabled by this, I'll refer to one technical manuscript that we published, which really reset expectations of what is possible in the industry today. This was worked on IBM processors, and I'll just read out the title. Quantum optimization using a 127-qubit gate model, IBM quantum computer, can outperform quantum annealers for non-trivial binary optimization. Now, up until the paper, this particular paper was published, annealers were the only game in town, truly, for quantum optimization. And this paper turned that upside down. Some of the problems that we focused on start in what's called QUBO, quadratic unconstrained binary optimization. The experts in the room will be familiar. And a canonical example of this is something called max cut. This is a problem where it can be represented as a graph, And your task is to turn that graph into two graphs by cutting as many lines as possible. Maximum cut, max cut. Now, you can intuitively see that if the problem is small enough, it's not so hard to figure out. But as the number of graph nodes grows, as your problem gets more complex, it becomes a very challenging problem to figure out how to do this. So we went and looked at max cut problems using our solver on IBM's processors. We looked at arbitrary graphs, not for the experts graphs that were linked to the underlying architecture of the device. And we first said, how well after we run the optimization does our answer represent the max cut? In this particular distribution, which you get from the plain vanilla implementation, the bare hardware, if you will, the results are no different than random selection. Errors have overtaken the outcome. And it does not at all overlap with the true max cut. We know what that is because the problem is sufficiently small that we can run a classical optimizer. But using exactly the same hardware and just our solver on top of it, this is the change. You shift the distribution of outcomes all the way so it's stacked up against the true max cut. It's a massive enhancement. This is run on 156 qubits. It uses the entire device, and it's a classically non-trivial graph. It really works. What I want to emphasize here is that we're not just running an optimization. We are successfully solving the optimization. We are getting the right answer with unit probability. In that manuscript, we also looked at another class of problems, hobo problems, higher order binary optimization. And here, there was a great amount of published work from the Los Alamos group comparing IBM processors and others to D-Wave annealers. And it was indisputable in that previous publication that the D-Wave annealers were far better than the IBM implementation. With our solver, that's no longer true. In this particular use case, we showed that we could, again, shift the distribution to get the right answer, and even get the right answer, successfully solve the problem in cases when the annealers didn't get the right answer. They came close, but didn't. Now, this was a fundamental change in what we believed these machines were good for, the gate model quantum computers and optimization. But I want to emphasize very clearly that we were extremely careful in our publication to not claim all annealers are dead or anything like that. We have shown in certain cases that a gate model machine can outperform an annealer. We've shown that they're now competitive, and D-Wave was actually good enough to validate this independently on the same exact test cases. But as we look ahead now, we have to think about solving much larger problems with much larger quantum computers. And here we have to move beyond what are called error suppression strategies I've told you about so far, to think about incorporating quantum error correction. I think everybody is familiar with this notion, the algorithm that we can use to identify and correct errors. We believe it is the union of these two technologies that can bring us to large-scale advantage. And I do have some maybe bad news for the audience. Despite the excitement in the scientific community about demonstrations of quantum error correction, this technology is not able right now to deliver you practical benefits. It actually generally makes things worse. And that's because it is so resource intensive. Something like 99.9% of your processor is or will be dedicated to nothing more than running quantum error correction. Now, if you have 1 billion qubits, maybe that's not so bad. But if you have 100, that means your whole device is dedicated to quantum error correction. In the Google example, they were able to achieve a factor of 2 improvement in performance of their hardware by consuming all 105 qubits on the device. This is a huge penalty that means you're not getting value. And the way we think about it is that it's silly to just run quantum error correction natively, or in a bare sense, on hardware. It's a little bit like this analogy, which should be understandable in Dubai. It's like turning on the air conditioning with all the doors and windows open. Doing so doesn't make the room very cool. It's extremely inefficient, ultimately not very successful. But combining error correction and error suppression is as simple as closing the doors and windows, reducing the heat leaks in this analogy such that quantum error correction is more efficient. With that understanding, with that realization, we began exploring how we can integrate quantum error correction in its piecewise form in order to deliver actual value. not to do science demonstrations, to deliver actual value. And so we're very excited that we're getting close to releasing the first quantum error correction primitives in our error reduction software, or performance management software, that delivers net advantages for the end user. We do this by focusing on primitives, things like parity checks, without doing full encoding. And this has allowed us to show some extraordinary things, in this case, generating a large-scale entangled state where we can reduce the impact of bit flip errors, so our fidelity goes from 2% to 99.5%. And we do this using only 1% of the overhead that's typically required for quantum error correction. A very, very small amount of resources dedicated to giving these huge benefits. And this has also let us set a wide variety of records. Using this concept, combining error correction primitives and error suppression, we have set the world record for the largest verifiable entangled state, 75 qubits on an IBM processor. We've done teleportation over 40 qubit sites on, again, an IBM processor with 85% fidelity, and we've cut the overhead required by 100x. Now, all of this is driving towards the idea that we don't just have to get to break even in quantum error correction. It's not enough to not make things worse. It's also not enough to make things just a little bit better. We have to get to a point where quantum error correction is the technology of choice in delivering improvements to processors. That's what we call quantum error correction advantage. It's our objective to push there, and with the demonstrations that I've just shown, I hope we've convinced you that we're getting closer and closer as we get every bit of performance out of those machines. But just one more thing. I gave a prelude yesterday that I was going to share one additional insight about the work that we've been doing. And here we turn to the other part of our business in quantum sensing. Where, as I mentioned yesterday in one of the discussions, many of the problems are extremely well defined. The problem that we're particularly interested in is how do you navigate when GPS is not available? In particular, when GPS is denied by jamming and spoofing. This is something that has become a major challenge. I'm sorry, I may ruin your day for those of you who have to fly out soon, but over 1,000 flights a day are disrupted by GPS jamming since March 2024. It started and grew very rapidly, very recently. The biggest jamming incidents are in the Middle East, over the Black Sea, over Ukraine. It's in all the areas where we have major commercial aviation routes. Q-CTRL has invested very heavily in becoming a leader in a new form of quantum assured navigation. And we do this using something called geophysical map matching. By analogy, it's like the game that many of you may have encountered in the Scouts of orienteering. Given a map and your eyes, you have to locate landmarks, find out where you are on the map, and then navigate to a particular location. We have brought orienteering into the quantum age, and we do this with something called MagNav, magnetic navigation. Earth's magnetic field doesn't just point north, it has all sorts of bumps and wiggles that come from the structure of Earth's crust. These are unique fingerprints that we can use if we have the right eyes to see these bumps and wiggles. For that, Q-CTRL has built extraordinarily sensitive, very stable magnetometers, and software which allows us, just like in the quantum computing case, to mitigate the impact of interference and noise that comes when you take an instrument like a quantum magnetometer that's ultra-sensitive and you put it on a moving vehicle, like a boat or an aircraft or a road vehicle. Software is a huge part of this. We began a partnership that we announced last year with Airbus, looking at bringing a new generation of flight safety technology to commercial aviation and also defense applications. And we began a series of flight tests where the pilot had a good time in this particular route. This is from FlightAware, where we were examining how well magnetic navigation could work in the real world. And so the exciting one more thing is we have indisputably achieved quantum advantage, true commercial quantum advantage in a critical mission where the problem is well understood. In this particular example, using magnetometers, quantum magnetometers on the aircraft, and comparing against the best classical backup, which is an inertial navigation system, we achieve a 50 times quantum advantage. Over a 500-kilometer long flight, our positioning uncertainty is 100 meters at the end of the flight. Not only is that way better than the direct comparison head-to-head we did, it's better than using classical magnetometers, and it's better than the best alternative technologies that are not really compatible with this platform. Things like Doppler ranging or LiDAR ranging. We are now at a stage where quantum advantage is not only a hypothetical that we're aiming for, it is something that is here right now. Thank you. We're very excited to announce this formally next week, but you are the first audience to get a real taste of it. We wanted to share it with you as we begin our relationship building in the region, because there's so much we can do together. So thank you all very much for your attention. Look forward to talking to you.